Today's lesson is on complex numbers and how they relate to the polar coordinate system and something called DeMoivre's theorem. First, we are going to be graphing complex numbers on the complex plane. Okay, complex plane is going to look like a plane, but rather than it representing a x and y, this is going to be the real axis. So I'm going to put a R there to say real, and then this is going to be our imaginary axis. So I'm going to graph some imaginary numbers. Say I had the complex number 2 plus 3i. So this is what a complex number looks like. I'm going to go 2 on the real axis and 3 in the imaginary axis. Okay, and it will match coordinates. So say I have -3 minus I. That's going to go back 1, 2, 3, and down. Okay, we can graph what's called a pure imaginary number. So 2i would be 1, 2 up there on that axis. Or we can graph real numbers. 1, 2, 3. So that's how we graph. Now we're going to calculate the absolute value of the complex numbers. And this is going to be the distance from the origin. Okay, which is really what absolute value is. It's how far away from center. So 3 is 3 units away from the origin. -3 is 3 units away. So the absolute value of a complex number, a plus bi, if we're just looking for the distance, we're just going to use the Pythagorean theorem. So the square root of a squared plus b squared. Don't include the I. The I is not a part of this, but we're just using the Pythagorean theorem. Okay, so we're going to find the absolute value of 2 plus 3i. So that's going to be the square root of 2 squared plus 3 squared. So square root of 4 plus 9, which gives us the square root of 13. Now we're going to tie this back to polar, the polar form of complex numbers. So let's say I have some x plus yi. Okay. Well, we're going to use our conversions. X is equal to r cosine theta, always. Y is equal to r sine theta, always. Now what I'm going to do is factor out the r, and I'm going to put the I in front of the theta. Okay, this is the polar form of a complex number. The r is the absolute value, also known as the modulus. Okay, and then the theta is either the amplitude, or sometimes you're going to see it as the argument. Couldn't tell you why. I'm just interested, do you know it's r and theta? Okay, now we're going to convert complex numbers. The good news is this is going to follow exactly what we were doing with rectangular and polar coordinates. It's just it's representing complex numbers rather than a coordinate. first direction we're going to go is starting with a rectangular complex number and ending up with a polar complex number. So starting with an x and a y and ending with an r and theta. R is going to be the square root of x squared plus y squared, just like it does with the coordinates. Theta is going to be the tangent inverse of y over x in the correct quadrant. So let's see some examples. I'm going to start by converting to polar. So I have the complex number 8 plus 8i, and I need to find the r, and I need to find the theta. R is going to equal the square root of 8 squared plus 8 squared. So that's the square root of 64 plus 64, which is the square root of 128, which does simplify, or you can leave it just like that. Theta is going to be the tangent inverse of 8 over negative 8, which is going to be the tangent inverse of negative 1. Then we go to the unit circle. Okay, by now you should have added the tangent values to your unit circle. There are two locations where our tangent is negative 1. That's going to be at 3 pi over 4 and at 7 pi over 4. So which one is correct? Well, if I were to graph 8 minus 8i, or 8 plus 8i, we're here in the third quadrant. So my correct theta will be 3 pi over 4. Now when we're doing coordinates, we put these in parentheses and went from here. We're talking about the complex numbers though. So it's going to be r, which is root 128, in parentheses, cosine 3 pi over 4 plus I sine 3 pi over 4. Okay, and that is our answer. It looks complicated, you know, complex numbers and all. So this is what you'll see. Sometimes you'll see books do like root 128 and then do CIS the value, but we're going to use this whole thing. Okay, now I'm going to convert negative 6 to a complex number, or to a polar form of a complex number. Well, negative 6, if I were to graph it, would be down here. I'm not going to use the formulas, you could, but what I'm going to use is my knowledge of the polar coordinate system and how this works. So my r, the distance, is going to be 6. The absolute value of negative 6 is 6. My theta, sorry, I did 6i. Negative 6 is down here. Apologies. My theta is going to be the angle here. So that's, for this, is going to be pi. So negative 6 as a polar form of a complex number is going to be 6, then in parentheses, cosine pi plus I sine pi. And we'll get to why would you want to do this to a negative 6 shortly, but that is our answer. Going the other direction is really pretty easy. You're going to do the math that you feel like you should be doing the whole time. All you're going to do is simplify the expression. So I'm going to convert to rectangular form. So this is the polar form, and we're simply going to simplify. I'm going to start on the inside using the unit circle. Cosine of 5 pi over 6 is a negative root 3 over 2, plus sine is 1/2. Don't forget your I, and then distribute. So 1 times negative 3 is negative root 3 over 4, and then distribute. We're not using 1/4 I. and that is the rectangular form. So before we move on, I want to just differentiate between coordinates and complex numbers, because the math we're using is pretty much the same thing, so it can get a little confusing. For coordinates, the rectangular coordinates are x comma y. Polar coordinates are r comma theta. There's no, it's the parentheses, comma, and so on. The complex numbers are x plus y I and r cosine theta plus I sine theta. So they're different. They don't mix and mingle. Complex numbers are complex numbers, coordinates are coordinates. Okay, so the answer to why you would want to put a number, a complex number in polar form, comes from certain operations are easier to do in polar form. So we're going to start with the product of complex numbers in polar form. So we're going to take a generic polar number. So we'll have r1 cosine theta 1 plus I sine theta 1. And we're going to multiply that by another one, r2 cosine theta 2 plus I sine theta 2. Okay, to do the product in polar form, we're going to take the two r values and multiply them. And we're going to take the two theta values and add them. Okay, so we multiply the r's, add the thetas, and we'll have our product. So let's do an example. We have 7 cosine 7 pi over 12 plus I sine 7 pi over 12 times 3 cosine pi over 12 plus I sine pi over 12. Okay, so the multiplication is really easy. We're going to multiply the two r's, so we'll get 21. And we're going to add the two thetas, so 7 pi over 12 plus pi over 12 is 8 pi over 12. Okay, so in this step, we have multiplied them, but we're going to turn this back into a rectangular number. So we'll first reduce these fractions. So 8 pi over 12 is the same as 2 pi over 3. Okay, and then we're going to use the unit circle to evaluate these two. Cosine 2 pi over 3 is a negative 1/2. Sine is a positive root 3 over 2. Don't forget our I, and then distribute. So our product here is going to be negative 21/2 plus root 3 over 2 I. So here's another example. We have 3 cosine pi over 12 plus I sine pi over 12 times 5 cosine 5 pi over 12 plus I sine 5 pi over 12. So I encourage you to pause and attempt this product on your own. All right, so again, we're going to multiply the two r's, 3 times 5, and add the thetas. So pi over 12 and 5 pi over 12 is 6 pi over 12. So that'll be pi over 2. Then we evaluate. The cosine value at pi over 2 is 0. The sine value is 1. So this is going to be 15i as our final answer. Now we're going to look at the quotient of complex numbers in polar form. And this will follow what we did with the product. So we're going to have R1 cosine theta 1 plus I sine theta 1 over R2 cosine theta 2 plus I sine theta 2. When we multiplied the r's. When we divide, we're going to divide the r's. When we multiplied, we added the thetas. When we divide, we're going to subtract. To get our new value. So let's do an example of division. So I have 10 cosine 3 pi over 10 plus I sine pi, 3 pi over 10, and we're going to divide that by 2 cosine pi over 20 plus I sine pi over 20. So before I do this, I'm going to get a common denominator since I'm going to have to subtract. So I'm going to make this 6 pi over 20. Okay, so we will divide. 10 divided by 2 is 5. And subtract 6 pi over 20 minus pi over 20 would be 5 pi over 20. Reduce those fractions. So this will be pi over 4. We're going to have root 2 over 2 plus root 2 over 2i, and then distribute. So our final answer here will be 5 root 2 over 2 plus 5 root 2 over 2i. Okay, last we have DeMoivre's theorem. So DeMoivre's theorem is how to do a power in complex numbers. So we're going to take r cosine theta plus I sine theta. We're going to take this complex number and we're going to raise it to a power. This will follow what we did with the product and the quotient. So when we multiplied, we multiplied. When we divided the r's. For a power, we're going to raise it to the power. Okay, and then you can probably predict when we multiplied, we added. When we divided, we subtracted. When we're raising it to a power, we're going to multiply. So we're going to multiply the theta by whatever the power is. And this is called DeMoivre's theorem. Okay, so this is where the power of the complex numbers really comes in. Because when we multiplied and we had two rectangular, you could multiply those, you just FOIL and go on your way. Dividing, you can do using conjugates, but a power, if I wanted to raise this to the fifth power, I would have to write out 1 plus I times 1 plus I times 1 plus I 5 times and then go through that algebra. For polar, all I have to do is convert the value to polar, do this simple little formula, and we're done. Okay. So the first thing we need to do is convert to polar. So I'm going to take 1 plus I, get my r, which will be the square root of 1 squared plus 1 squared. So we get the square root of 2. Theta is going to be the tangent inverse of 1 over 1, which is 1. And we're in the first quadrant, so this is going to be pi over 4. So my new problem is root 2 cosine pi over 4 plus I sine pi over 4. We're taking that and raising that to the 5th power. Okay, so we're going to have root 2 to the 5th power, and then we're going to multiply. So we're going to have 5 pi over 4 plus I sine pi over 4. Okay, so we've done the math here. Now we just need to convert to rectangular. So I'm going to leave this alone for now. Cosine 5 pi over 4 is negative root 2 over 2. Same with sine. Okay, so then I'm going to multiply in. So I've got root 2 to the 5th. So this is now going to be root 2 to the 6th over 2. Well, I could rewrite this as negative 2 to the 6 over 2. Okay, which is really 2 cubed. So 2 cubed is 8. So we're going to have a negative 8 over 2 minus 8 over 2i for a final answer of negative 4 minus 4i. Okay, so we did the power in this one step, but in order to do that, we have to convert. So let's do another. Again, I encourage you to pause and try this on your own. Our first step is to convert to polar form. So we're going to get our r, which will be the square root of root 2 squared plus root 2 squared. So that's going to be 2 plus 2 is 4. Square root of 4 is 2. Theta is going to be the tangent inverse of root 2 over negative root 2, which would be the tangent inverse of negative 1. And we're looking in, this is a negative positive, so we're looking for where it's negative 1 in the second quadrant, which is going to be at 3 pi over 4. So we're going to rewrite this problem. Our new r is 2 cosine 3 pi over 4 plus I sine 3 pi over 4. All of this raised to the 5th power. So we're going to have 2 to the 5th cosine multiply 15 pi over 4. All right, so again, we've done the power. Now we just have to simplify. 2 to the 5th is going to be 32. 15 pi over 4 is not on the unit circle, so we need to find a coterminal that is. So we're going to subtract 2 pi, which would equal 8 pi over 4. So I'm going to subtract 8 pi over 4 from 15 pi over 4 to get 7 pi over 4. And then unit circle. So cosine 7 pi over 4 is a positive root 2 over 2. Sine is going to be a negative root 2 over 2. And then distribute. So our final answer is going to be 16 root 2 minus 16 root 2i. Now I've got the 4th root of negative 1 plus root 3i. So we're putting this here because I can still use DeMoivre's theorem, because I can rewrite the 4th root as the 1/4 power. So we're going to convert the negative 1 plus root 3i to polar. Our r will be the square root of 1 squared plus root 3 squared, which is going to be 1 plus 3, which is root 4, which is 2. Theta will be the tangent inverse of root 3 over negative 1. So we're looking for the tangent inverse of negative root 3 in the second quadrant. So in the second quadrant, tangent is negative 3 at 2 pi over 3. Okay, so again, make sure you have those tangent values on your unit circle to make life easier. So I'm going to rewrite the problem as 2 cosine 2 pi over 3 plus I sine 2 pi over 3 to the 1/4 power. So I'll do the power. So 2 to the 1/4 cosine, when we multiply 2 pi over 3 times 1/4, that'll be 2 pi over 12. Which will be 2 to the 1/4 times the cosine of pi over 6. Now the sine and cosine of pi over 6 we can get from the unit circle. But this 2 to the 1/4, you'd have to use a calculator to evaluate. So if you do that 2 to the 1/4 times this, we'd end up with 1.03 plus 0.59 I. So you want to keep it exact if possible, but if you can't, then that's what we can do. So that is the complex number of the polar form of complex numbers and the operations that we can do once it's in that format.